Okay, welcome everyone. Let's wait for a couple more minutes for more students to join. Yeah, thank you for turning on the video. So perhaps I will start at around 12:04, 12:05 to let more students join. Today's lecture will be rather short. We only have 16 slides, as you have already seen. And before we start, I know that when we have the Zoom lectures, you tend to use like a raise hand function, but when I'm using this laptop right now, normally I can easily see your hands, raise hands in the chat window. But in this lecture, I'm just using one laptop here, and it'll be very difficult for me to track. Once I share the full screen, it's very difficult to see the raise hands. So if you can either raise your hand, stop me verbally, just ask me, let me know if you have questions, then we can probably solve that on the spot. You can try to type in the chat, but if I respond for about 2 or 3 minutes, you can imagine that I cannot see the chat window at that particular point. So then please stop me by speaking out, all right? Okay, I think we have 10 people, including myself. Can I ask you to turn on the video, like I said? Not to microcontrol you, but just to check the response from the audience. All right. Right. Ryan, Andrea, can you please turn on your video? Thank you so much. All right, there are some students who are who asked there's a conflict in the schedule, so I intend to record this session. Don't worry about the video; it's more about the slides and the content itself. And then I'll try to figure out how to upload it into the Luminous. If the uploading is not going to work out, then what I will do is that I will either share the recording link to the Zoom, or I'll try to dip into my previous recording in the last semester and see which one is better. But I think I anticipate that today's recorded lecture in the Zoom can be shared. All right, so before I start, any questions or comments you have? So Stephen, is the voice clear? I know I can see that you're outside. Oh, I cannot hear you, sorry. Okay, very good. All right, so let me then start the lecture. I will start the recording first.
Recording in progress.
And then my screen. Please let me know if you can see my screen. You can probably say, okay. All right, Joshua, can you see my screen? Okay, very good. All right, so let me start the lecture today. Today's lecture is about bias circuit. So until today, we have learned about how to design an amplifier, and then we had the VB, such as the DC source, to be used. But as I said, for the final project, I anticipate you to use single power supply, and only exception is the input. If you can use the input DC bias point, that's allowed. But other than that, you should generate all the bias circuit needed yourself. And pertaining to that, we'll be learning about how to generate the bias DC voltage, in other words. Okay, let's see. And this is the outline. We have the introduction to the bias circuit. And then I will go on to the supply independent current source. So when I say supply independent, okay, let me see if I can draw here something. Probably better use the PowerPoint. Hold on a second. All right. When you see the VDD, design the VDD in a system, this is the VDD. And over time, this is what you're anticipating. Let's say 1.8 volt. 1.8 volt. Over time, you anticipate that'll be 1.8 volt. But if you have measured a supply from the lab, you know this is not necessarily the case. The actual VDD, for various reasons we will be covering, the actual VDD looks something like this. Let me see if I can change my color. Will be changing over time. Okay, it's the matter of the amplitude in the change of time, but we cannot deny the fact that the VDD will fluctuate. Okay, I think I should turn off my background. Okay, hold on a second. Okay, yeah, so the VDD will fluctuate over time. And if you have a source, let's say VB, that you used to have in your schematic, that is dependent on the VDD. Then if the VDD fluctuates, so will the VB, right? The bias point will fluctuate. And by now, you already know what will happen if the fluctuation of the supply will be, and also the bias points. Even the small change in the bias point that goes to the gate of a transistor will significantly change the bias point, because as you know, in device in saturation, the drain current changes squared to the gate voltage. You already know this. This is called the drain current equation, right? So if you have a small fluctuation in the gate, that will abruptly change the bias point, and you don't want that situation. So that's why we say, okay, we want to have a supply independent current source. And then also the third type is the constant GM bias. This is saying that, oh, okay, we can generate a circuit that has the constant GM, and then use that as a bias circuitry. So those are the things that we were learning today. So let's first go with the introduction. Okay, we see that transistors in the analog circuit need to be biased in a certain operation regions. And when it comes to EE3408C, we already have seen that you want to bias transistors in saturation, right? That means the gate voltage has to be biased in a certain manner, that design point or intended point. And both the voltage and current source can be used for this manner. You can use the voltage, you can use the current. So for example, if you have the current source, that means you are using a current source as a biasing point that will be connected to the drain of a transistor. Or if you're using a voltage source that goes to the gate of a transistor, then you're going to bias the transistor by controlling the voltage in the gate. And the bias voltage and the current leads need to be very stable. As you can imagine, if you have designed that, okay, my gate voltage should be 0.9 volt, then by right, you need to have 0.9 volt as stable as possible. And ideally, it's independent of PVT. So you might have heard about this in my previous lectures, but this is a standard term that analog designers use. We call it PVT, which stands for the process, voltage, and temperature variation. And what it means is that process variation is you have designed a transistor, let's say with the aspect ratio of 100, but due to the process variation during the fabrication, there are many factors that alters the slight changes in the dimension. And one transistor will be having a gate length of, let's say, 0.5 micron, whereas the other one, which you drew this transistor to be 0.5 micron, but actual dimension will be, let's say, 0.499998 micron, right? And those are process variation. And so is the width. You have designed the width to be 100, but one transistor will be 100.0001, the other one will be 99.99997, and etc. Okay, in engineering sense, we regard it as 100, but the actual characteristic of a transistor will be slightly different. That's called the process variation. And so is the voltage. As I already pointed out, we intended to have the supply of 1.8 volt, for example, but due to many noise, coupling, and many factors, that 1.8 volt will change. And I'm telling you, this will not be the same for each circuit, so that it's close enough to the intended process design point, but it'll be slight changing. There will be slight changes and differences between the circuits. And lastly, it's temperature. Okay, the temperature we didn't cover so far in the project, and we will not cover it because by default you are simulating your circuit without anything changed. We are assuming that you're running this temperature of nominal room temperature, and in circuit design, when we say room temperature, that's 27 degrees Celsius. Okay, maybe in Singapore that's a reasonable assumption that the room temperature is 27 degrees Celsius. But let's say I used to live in UAE, United Arab Emirates, and in that case, the room temperature may rise. The environment temperature may rise up to 50 degrees Celsius during the summertime, and it may go as low as 14 degrees or even lower. And let's say you're in Alaska, right? During the winter time, the environment temperature may go to way below 0 degrees Celsius. And if you look at it, the temperature will affect the drain current because it will first of all affect the mobility of the holes and electrons, and the threshold voltage is also slightly affected by the temperature. So this means that you have designed a transistor with a W of L with intended drain current of 1 micron, but as the temperature fluctuates, that drain current may fluctuate 200% or go as low as 50%. And your product, this is why part of the reason during the lecture some time ago, I told you that your smartphone is not designed to designed to guarantee operation below sub-zero and above 40 degrees Celsius. And that's because of this temperature variation, right? Because of design margin, the smartphone will operate, but you cannot sue the manufacturer, say that you have operating this smartphone in minus 10 degrees Celsius, and it didn't function as normally. You cannot sue, because if you look at the manual, it tells you the operating temperature is between 0 to 40 degrees. Now, usually a reference current or voltage is needed to define a biases. This is what I mentioned in the previous slide. And a band gap reference with the low temperature dependence is often used to generate the reference voltage. What I mean by that is that you rely on a band gap. Okay, band gap of a silicon is a defined value, and it has a very low temperature variance, meaning that even if you change the temperature a lot, the band gap voltage will not change that much. Typically, it's no more than the ppm, parts per million. So that's why we typically use the band gap as a reference. You might have heard about that. We'll come back to that. And any questions up to this point? Okay, let's move on. Let's first look at the simple bias circuit. I'm sorry for this title page being a little bit hidden. I don't know how to get rid of this bar. Oh, here we go. This is the simple bias circuit. So now, by now, this looking at the schematic, you as a 3408C student, you now don't panic. You know what's going on here. And there's a V in. Oh, sorry, I didn't mention V in is here. There's a first stage differential stage with the M3 and M4 as the current source as a load, active load. And the second stage is the common source amplifier defined by the GM of M6 and goes to the B out. So now, where is the bias point? Can anyone tell me where the bias is in this circuit? It's a very simple question, right? Brandon, can you give me some insights? Do you see any bias point or bias voltage here?
For M6, is it?
Yes, the M6 is the amplifying transistor. I'm talking about the bias. Bias refers to, let's say, you need to apply certain DC voltage to have the transistor in saturation.
It would be with the V in.
V in, yes, that's definitely the case. Any other DC points that you might want to check?
The one at the drain of M4 has to be
M4
in,
drain. Yes, that's also true.
and the
Okay,
VB.
that's right. That's the most important thing, the VB. Thank you, Brandon. So you can see there's a VB. And by now you already know, where does the VB come from? The easiest solution is that you have the DC source attached. But as I said in sub-project 3, I don't allow you to use a DC source for VB, for example, in the footer. So we have to actually generate ourselves the VB, right? That's called a bias circuit. So for this OPM, we only need one DC bias, that is VB, to provide a DC bias current to our transistors. But in sub-project 3, I don't even allow you to use this additional DC bias source because you already have the VDD with the DC source. So input DC is usually provided by the preceding stage, including the signal source. This is the exception in sub-project 3. You can use the DC source for the input to bias M1 and M2, but that's about it. VDD and the input, that's the only DC source allowed to use. So how do you then generate the VB or the bias circuit? Anyone? Okay, let's say, Celine, do you have any insights here?
For VB, can we just use 2 resistors?
That's another option. That's definitely another option, right? That's a good option, by the way. Can anyone tell me what's the issue, potential issue of using voltage divider for VB? Stephen? Don't worry if you get it wrong, it's fine. Or Wei Chao, would you like to give me some insights? The question is, what would be a problem if you use the voltage divider to provide VB?
I have against both. If no
High DC resistance.
Sorry.
Yeah, DC resistance is, so for example, let's give you an example, right? Let us say that intended VB point was 1 volt, right? What if you have 2 high resistance values, let's say 1 mega ohm and 1 mega ohm, with a 2 volt supply, and then give the voltage division to the input of the VB? Theoretically, it should work, right? But there are potential problems with this. Any question or any comments you have?
Is it a PVT?
That's right. That's PVT variation. And can you, Celine, so can you tell me what's the PVT variation with the impact of here? There are 2 problems actually.
Maybe temperature change and the resistance can change.
Yes, temperature does impact the resistance, but that is not as great as the other variation, the process and the voltage variation. So let's look at it. I said you're assuming 2 volt in the supply. But as I said, the 2 volt is not going to be 2 volt stable. It's going to fluctuate. And if you use the voltage divider, what happens if you have a fluctuation supply? The corresponding divided voltage will also fluctuate. And as you can see, that goes to the M5 and M7 gate. And as I told you in the beginning, a slight change in the gate voltage will quadruple, affect the drain current in quadruple because there's a square term. That's one problem. Second problem is the process variation. I said there'd be 1 mega ohm and 1 mega ohm resistance. But that's in the schematic stage, you have designed 1 mega ohm and 1 mega ohm. But by the time you fabricate, these registers may be one on the upper side will be 1.0001 mega ohm, and the one on the bottom can be 0.9998 mega ohms. In engineering sense, they are both 1 mega ohms, but we cannot deny the fact that slight change will fluctuate. I mean, will change the design point in the VB, right? Those things are a problem. So voltage source, you can probably use a precision voltage source like VB from the external, which I don't prefer because obvious reason. First of all, you need to have a separate DC source, which is not easy to get. And this using a VB outside is still problematic because once you fabricate the chip, right? You have fabricated chip. This one on the rectangle inside the red rectangle is on chip. And there's no way what drain current corresponding to the VB that you're providing externally will be. Why? Because there's no current meter inside the chip. Do you understand? Once you have applied the VB, you only have a wild guess what the actual drain current will be correspondingly flowing. You know the approximate amount, but you don't know what's the actual current flowing because you cannot tap into the chip. Unlike in the schematic, in the cadence, you can tap into the chips and then measure what it simulate what's inside, because you cannot open up physically the chip, right? Now, with that, what we can do is that the wild guess is that the drain current with the drain current equation, you can guess, estimate what the current will be. But after chip fabrication, the exact ID is unknown because, as I said, you cannot tap into inside the chip physically. So the second option that we have learned was to use the current mirror, because even inside the chip, in this case, you will know what the drain current will be, because with the matched M7 and M8 and M5, as far as the IR is known, the same corresponding current will be flowing in the chip, because that's the current mirror, right? And do we know what IR will be? IR, you can actually measure it because it's outside the chip and you have the supply voltage known, and you can measure this point. You can measure this node, that is the input terminal of the chip. The voltage difference between these two divided by the value corresponds to the IR. And then once you have the IR, that is actually the ID5, it's the same amount. So the second option is preferred method, right? In this case, if you have a different aspect ratio between M5 and M8, we already know the drain current is proportional to the ratio of the M8 with respect to the M5. M5 with respect to the M8. Any questions so far? Andrea, do you understand what I'm trying to say? Okay. So IR can be measured since it's off chip, whereas one on the left, drain current cannot be measured because nothing that you can measure except the VB, but you cannot correspondingly measure the current itself because you only have the ratio and you have the equation that will approximately let you know what the drain current will be on the one on the left. So here it comes the topic of the supply independent current source. As I said, one of the reasons you don't want to use the voltage divider is because you don't want to have the fluctuation of the supply affecting the drain current. So if you had a supply independent current source, probably that's a good news. The current is actually independent of the supply change. Even if there's a fluctuation in the VDD, this reference current will be constant. That's what we want. In the current mirror shown here, we assume that the reference current IREF is available, and that's the case. For example, the slide on the previous slide, we had the one register which you can measure the IREF. But if that assumption is true, the primary requirement for this reference current is that the output current, which is the drain current of M2, is insensitive to the supply fluctuation on the VDD. That's the intention of the using of the current source. And let's see how you achieve that. Now, the problem is, how do you then generate that such IREF? It's easier being said than done. In the cadence, you just pull up the current source and that's it. But in the practice, you cannot do that, right? So that's where we have the threshold reference current source as a starting point. So threshold voltage, this is coming from the idea that the threshold voltage of the MOSFET transistor has little dependency on the drain current. So what I mean by that, if you have a large drain current, let's say 1 milliamp or 10 milliamp, or you have a small drain current of 1 microamp, that drain current itself has little effect on the threshold voltage of a MOSFET. All right. So if you use that threshold voltage as a reference, then correspondingly you have a little dependency on the current for the reference circuit as well. So you can use that as a reference. So let's look at the schematic here. This is one type of a threshold reference current source. If you look carefully, the reference circuit, reference voltage over here is obviously this voltage, which is the VGS of the M1 divided by R2. That's what's shown here. And VGS1 is defined as the threshold voltage of M1 plus the overdrive voltage of M1. All right. And the overdrive voltage of M1 is shown as this equation. Where is that coming from? We already know this is from the drain current equation. Now, in this case, you can see that the reference is actually independent. I mean, this reference circuit is independent of whatever you're showing in the threshold voltage, because threshold voltage doesn't change that much with respect to the drain current. But one problem, we still have one problem with this equation, is that the reference current is still dependent on the drain current. The threshold voltage is not dependent on the drain current, but the term on the reference circuit, I mean, reference current still has the reference current over here. That's a problem. So your goal is to make this reference current almost independent of the drain current flowing. And by inspecting this equation, can anyone tell me how do you make it? Even if there's a fluctuation in the input, if you want to make that fluctuation to be insensitive as much as possible to the reference, what can we do? The hint is, you can see that the I in is divided by the K prime N W over L. And noting that K prime N is fixed value, if you have a really, really large W of L, then the fluctuation in the input will be divided by the W of L. So we can see that if you use a large dimension on the M1, then even if you have a fluctuation in the input current, that will be divided by the large value. So the effect of that change will be little, right? So practically what you can imagine here is that if you can choose large W of L, then the dependence on the supply voltage will be minimized, right? Why do we have a dependence on the supply? Because if you have a fluctuation in the supply, then the voltage drop across this R1 will fluctuate, which means that the input current will fluctuate as well. But because that will be divided by large W of L of M1, the effect of that fluctuation will be divided by the device dimension. So then you can minimize the impact of such change. That's what I'm trying to say. Is that clear, Brandon? Okay. Now, with using this, we can also induce the self-biasing current mirror. So it looks very strange. You have the diode connected M3 and diode connected M1 here, both having 1 to K ratio. For example, M1 being 1 and M2 being K. And you have a corresponding M4 and M7, which also has 1 to K ratio. And if we size the transistor in that fashion, you can see that the W of L of 2 is actually K times the W of L of 1. And WL of 3 is K times the W of L of M4. So in this case, if you neglect the channel length modulation, for the simplicity at this point, if you neglect the channel length modulation, in this case, the reference current will be K times the input current, right? Input current is here, and the M2 and M3 are K times larger, so the reference current will be K times larger as well. We already learned this. Now, this relation is valid for any input current, right? You can see that this is a first order equation. Iref is K times IN. That means even if Iref is 1 milliamp, 2 milliamp, 3 milliamp, you have corresponding I input. But our goal is to have a very specific I reference current, right? For example, you have designed a point to be 10 milliamp. You need to make sure this equation only holds for 10 milliamp. So that means we need to have another constraint, right? In other words, you have this first order equation. You need another constraint, and you just a meeting point. Crossing point is the 10 milliamp the design intended point. How do you do that? That's a good question to ask. And that's where you add this RS. Okay, RS is added. Now this schematic is somewhat similar to what you have seen in the quiz. By the way, I will return the quiz to you. Sorry for delay here. I'm traveling, so once I get back, I'll return the quiz to you. But anyways, this inserting this RS and then tweaking the ratio to be 1:1 here on M4 and M3. If you compare this with the previous slide, M3 was K times greater than M4, whereas in the next slide, you now have RS added, and that side, the M3 is now 1:1 compared with the M4. So let's see what's the difference in the analysis compared to the previous slide. Now the register RS is inserted to define the current Iref. And how do you calculate Iref in this case? Okay, who didn't I ask? Okay, Dan, could you please give us some insight how we calculate IREF in this circuit? Okay, maybe his sound is not working. Let's see. Ryan, I'll give you a hint. This node that I'm circling here in the source of M2, using that voltage, how do you know IREF? It's okay if you get it wrong. Can you please?
Phi IM2.
Sorry.
Phi IM2.
The source of the M2. If you know the voltage of source of M2, that voltage divided by RS is the IREF, right?
Yeah.
And how do you know the source voltage in M2? Okay, let's get back to that. First of all, let's using this ratio of M1 and M2, we first get the relation that WL of 2 is actually K times WL of 1. And if you look at the M3 and M4, both the M4 and M3 have same ratio. That means input current is the same as the IREF, because M3 and M4 have the same ratio. Correct? This is the current mirror. If you just look at M3 and M4, this is current mirror with the same aspect ratio. So then the input current will be the same as the reference current. In other words, the drain current of M4 is the same as drain current of M3. Now, for the transistor M1 and M2, they have different aspect ratio. So that means the VGS1 is this one, right? VGS1 is actually defined as VGS of 2 plus the source voltage. I repeat, VGS of 1 is the same as VGS of M2 plus the voltage drop across the RS, right? And that voltage drop across the RS is actually the voltage that we want to figure out, because that will tell you what the reference current will be. And if you write that in the mathematical equation, this is how it works. VGS of transistor 1 is the same as the VGS of M2 plus the voltage drop across the RS. And the voltage drop across the RS is defined as the current across the RS, which is IREF, multiplied by the resistance value. And if you plug in the VGS equation from the drain current equation, in other words, the overdrive voltage plus the threshold voltage, this is how it goes. So that VGS1 is on the left-hand side, and the VGS2 is on the right-hand side with the IREF RS. And as you can imagine, both sides has the threshold voltage. You can cancel it out. And what is left over is the IREF with the relation shown over here. It's nothing serious. We just got it from the fact that the VGS of M1 is the same as the VGS of M2 plus the voltage drop across the resistance. Now, if you look carefully, let's look carefully at this equation here. If you look carefully, there's no term related to the VDD. In other words, the reference current is now totally independent of the supply voltage. In other words, even if there's a fluctuation in the supply, that will not affect the reference current. Can you now see that? Stephen? Okay. Josia, can you see that? Very good. And Andrea? Can you see that now the IREF is independent of the supply? Okay, very good. Now, however, the IREF is still dependent on the RS value. And RS, let's say we designed it to be 1 kilo ohms. Although we designed it as 1 kilo ohm, because of PVT variation, this may be 0.9997 kilo ohms instead of 1 kilo ohm. And that small, I don't want to affect that, even that small error, I don't want to affect the IREF. Although it will be very minute change, but I want to even eliminate the small change in the IREF due to the PVT, the process and temperature variation. Right? So if I repeat, number 7, this circuit has an issue that the IREF will be same as Iin for any values. So we want to have another constraint. That's what we did here. We added the RS in the source of M2 to now have 2 constraints, and there's only a single meeting point, crossing point, and we have successfully achieved it. And we didn't only achieve a single point, but we made sure that the reference current is independent of supply. Up to that, we have achieved. However, there's still process and temperature variation due to the RS. Okay, so that's what we are learning next slide. How do we actually solve that? And before we solve that, another thing to remember is as follows. Okay, this relation, IREF is equals to this equation over here, has another problem that we have to think about. We call it startup problem. And startup problem is very common in many circuits. You might have to check. So before we power on, if you think about it, before you connect the battery, all the points will be 0 volt, right? And in 0 volt, VGS1 is 0 volt. I'm saying that the supply is not connected, battery is not connected to the circuit yet. Then the VGS is naturally 0. And VGS2 is also 0, right? If you go back, we have the VGS1 is 0, VGS2 is 0, and hence the reference is also 0 because there is no voltage connected. Then these two sides are also balanced. What I mean by that is that at this point of operation, if everything's 0, VGS1 is 2, VGS2, and the IREF is all 0, this equation still holds. So our intention was to have only single crossing point, but actually it has two crossing points. One is when you have intended bias point of, let's say, 10 milliamp. You satisfy that condition. But if everything's 0, which is the startup condition, it also satisfies. There are two solutions which satisfy this equation. Okay, and by the way, those 2 points are very stable. And what is the problem with that is that, okay, you start up the circuit, and okay, it sounds like, okay, let me give you an analogy. This is the energy. Y-axis is the energy, and this is the 0 voltage point, and your ball is in this 0 voltage point. And it's very stable point, it's saddle point, it's very stable. And unless you bring this ball across this mound, which is the intended bias point of 10 milliamp, right? Your circuit may hit this 0 voltage point, right? Because you have two stable points, you want to make sure this ball over here is going to be rounded up and then goes to the other energy point. And that's why, first of all, we need to have a startup circuit. All right. Okay, let me see if I can erase this. So the startup circuit is intended to bring this ball on the stable point of 0 volt to a certain operating point, so it'll go to the other minimum energy point that is intended operation point. All right. So how do you do that? But by the way, before we go any further, you might as well think, okay, this startup circuit we have to add must only operate during the startup. And preferably, that startup circuit shouldn't consume any power after startup is complete, right? Because that's an overhead. After starting up, that's an overhead. You don't want any bias current to flow through the startup circuit. And how do you design that? So I already mentioned here, the startup circuit should only function on 0 current state, which means that when you power up the circuit, and after starting up the circuit, it should go to 0 voltage. I mean, it should not consume any power. All right. Okay, let's see. Stephen, is that clear to you? Okay. Wei Chao, is it clear to you? So, okay. First of all, did you understand that the equation over here has 2 points, right? If you have everything 0, it's also stable or satisfies. And you want to make sure the ball on the stable point in 0 is not what you want, because you want to make sure the reference current is, let's say, 10 milliamp. You don't want this circuit to be stuck in 0 milliamp point. So you need to have somehow a startup circuit to bring that ball to some saddle point and then goes to the other stable point. That's what the startup circuit do. So let's see how you operate. This is how you're gonna analyze it. First of all, you look at the schematic. What do I say? Don't panic. Please do not panic. And if you look carefully, you will observe that M1 and M2, M3 and M4 is nothing but the circuit that we have already learned. This is a current mirror with the reference current generating. Then what is M6, M5, M7? If you look carefully, M6 and M5 is an inverter. Okay, maybe I should draw it the other way around. It's an inverter. And how does it operate? If M5's gate is 0 volt, then so is the M6 gate. If PMOS gate is 0 and the PMOS source is VDD, then the gate is VDD times, VDD voltage lower than the source. Gate is lower than the source, which means it will turn on the M6. If M6 is turned on, what happens to the M7? M6 is turned on means that M7 gate goes to VDD. If M7 is VDD, what happens? It starts conducting. And if it starts conducting, if you look at it, what happens? This node voltage in M3 will start going lower. The gate voltage of M3 will be decreasing in the voltage. And then once it reaches the point whereby the source of M3 is threshold voltage higher than the M3, because the gate voltage of M3 will start decreasing as M5 is conducting. At that point, M3 will start conducting, right? If M3 is conducting, so will M4 because it's a current mirror. And if M4 is conducting, let's look at it. What happens? What happens to this voltage? Because there's on resistance in M1, this voltage will start increasing. In other words, the gate of M5 start increasing. Okay, I will color it differently to avoid confusion here from this point. If M5 gate voltage increases, then what happens to the M5? Can anyone imagine what happens to the M5 if the gate voltage of M5 increases? That MMOS turns on. If MMOS turns on, what happens? The voltage at the gate of M7 will start decreasing. And if the M7 gate voltage decreases, M7 will shut down. If the gate voltage of M7 goes below the threshold voltage of MMOS, M7 shuts down. If M7 shuts down, then now you're already in a stable point because reference current and the input current is flowing as intended. And then you can see that there's no more current flowing through. There's no DC path whatsoever because M5 is shut down, M7 is shut down as well. Okay, I repeat this. Let me repeat this from the beginning. Okay, at the beginning, everything is 0 volt. Meaning, okay, where's my point? This one is 0 volt because nothing is powered up. And when you apply the supply voltage, then the source voltage of M3 is now VDD, source of M4 is also at VDD, but this one is still 0 volt. If this is 0 volt, then M5 is shut down and M6, because the gate of M6 is 0 and the PMOS source is VDD, PMOS gate is 0, then M6 will turn on. If M6 turns on, the gate voltage of M7 is supply, which means that M7 will turn on. If M7 turns on, the gate voltage of M3 start decreasing through this conduction path in M7. And once there is more than threshold voltage difference between the gate of M3 and the source, then M3 turns on. That's the point where this ball, which was in the 0, goes to the other side, intended operating point. Now what you need to do is that you need to make sure that startup circuit has to shut down after you have reached the intended IREF and IRIN. And how is it achieved? Once the M3 is conducting, so is M4. And if M4 is conducting, I'll color it differently. If M4 is conducting, the voltage at M1's drain will start increasing. And if that's the case, M5 will turn on and M6 will turn off. If M5 is turned on, the gate voltage of M7 will drop through the M5, and then M7 will correspondingly shut down. Problem solved. You have kick-started the circuit to have the IREF to be the current that you want. At the same time, you have now correspondingly shut down the startup circuit. Does anyone have any question at this point? Ryan?
No, it's fine.
Okay, and Celine? Is it fine? Andrea? Yes, I hear someone is having a question. Okay,
Prof,
anyways,
uh,
yes, go ahead.
Yes, I'm wondering because you mentioned that if the gate voltage for M7 goes down,
Mhm.
the M7 will shut down. But I don't understand why, because the M7 is in saturation when the drain voltage is the gate voltage.
Right. So you can think about it this way. M7, M5, and M6, for simplicity, is a digital circuit. It's an inverter and a switch. And instead of thinking about it in the saturation, triode, or cutoff, you just think about an NMOS transistor in this way, which is simpler analysis. Okay, so you can correspondingly think about this as a switch, whereby if you apply high voltage to the gate, it conducts, meaning the switch will close. And if you apply 0 volt to the gate of an NMOS, it will correspondingly shut down. It will cut off. I mean, it will turn off the switch. In that aspect, for simplicity, what you can think is that if you apply digital 1 to the gate of this NMOS will close the switch and then the current will flow. If you, however, remove that gate voltage in M5 and M7, then correspondingly the switch will open. And then you can stop flowing the current. Do you get it?
Yeah, I get it. Yes.
Yeah. And it's the opposite for the PMOS. If you have a PMOS switch like M6 over here, right? The way you can turn on the M6 is to make sure the gate voltage of M6 is lower than the source by more than threshold. Then the PMOS switch closes. If the threshold voltage difference is not met, then the PMOS will turn off. Okay, I see a chat window. Why is why does M5 being on the gate of M7 drop? Is it due to M6 being off? Why is M6 on gate voltage? Yes, that's right. Okay, so I think I should not skip this and I explain this one by one. So let's think about it. That's a great question. How do I erase this? Okay, give me a second. Oh, looks like I did it through the annotation. All right. Okay. If you look at this M5 and M6, let's do it one by one. We call this an inverter. Why is it called inverter? Because if you have a high input, it goes to the output of low and vice versa. So let's think about giving a high input. Right? High input means that you have VDD in the source of the PMOS and the gate is also VDD. So whose question was this? I think it was Wei Chao. Okay. Wei Chao, in this case, is PMOS on or off? Can you please tell me? Nothing serious, right? In order for PMOS to be on, you need to make sure the gate voltage is lower than the source. So the holes will be collected underneath the gate, right? But now there's no voltage difference between the gate and source of M6. Hence, the PMOS will be off. Can you see that? Now, let's look at M5 at the same time. M5, the gate voltage is VDD, which is way above the threshold voltage of a source. So that means M5 is turned on. So it means PMOS is off, NMOS is on. What happens? The output will be pulled down. If the input is low, it's the opposite. If input is low, which means let's say 0 volt, the M5 will be turned off because threshold voltage is not passed for the NMOS. But at the same time, M6 has a gate voltage lower than the source by more than threshold, which means PMOS will be turned on. In that case, the output of this inverter will be pulled up. Is that clear? All right, let's see. There's another question. Okay, I think that's it. All right, so let's move on. So you can see that the at power on, I already explained what's going on there. And if I were to add one more thing, practically speaking, you want to make sure that the M5 is much stronger than M6, unlike the normal digital circuit, so that you have a very little threshold voltage. Okay, this is actually out of EE3408C scope, but I will just give you add-on note then. Okay, when the circuit started, I already mentioned that M5 will turn on and then M7 will turn off correspondingly. so that this whole entire startup circuit in red dotted box will turn off from solve. Any questions so far? Josiah, is that clear? All right, very good. Now, with that, we can progress to one more circuit over here with the self-biasing current source. So let us assume, okay, for example, you have 2 amplifiers or 3 amplifiers, and you want to have a bias circuit of first, second, and third stage. Let's say first stage with 1 microamp bias, and then second stage with 2 milliamp. I mean, sorry, the first stage 1 milliamp, second stage 2 milliamp, and third stage 2 milliamp as well. Right? In this case, you can use the circuit that we learned, which is shown over here, and then correspondingly add other branches like M6 and onwards, right, to have the supply for the other stages as well. So for example, if you added M6 and M5 on top of what we have seen in the previous slide, you can use M6 drain as bias 0.1, M5 as bias 0.2. If you need more, you can add one more stage to provide current that copies the reference to the corresponding stages, as many as you wish. All right. So in this case, the self-biasing current source can be mirrored to generate many current sources and branches, or sinks if you want. So for example, if you are using M5, that means you have the CMOS. If you are using M6, which means that the amplifier transistor will be an MOS transistor, right? We already know that from the previous stages, like a single stage amplifier as well as OPM. So in this case, if I were to do some further analysis, you can see that the bias 1, if you look carefully, bias 1 is done by the M6, which is copied from M3 to M6. And the ratio of M6 to M3 will definitely define the bias 1. So it means that the reference current flowing through the M3 drain multiplied by the ratio of M6 and M3 will be the bias circuit in bias current in M1, M6, sorry. And if you look at the bias 2, that's the ratio of M5 and M1 multiplied by the input, right? Because the input is the diode connection here, as you can see. And then you plug in this input current, if you look carefully, is actually the ratio of reference and input current over here. So if you were to get the relation of reference to the input, that's actually the ratio of M2 to M1. So then that's why you can see, it's ratio of M4 to M3, because M3 and M4, the drain is the same, and we have did this analysis before. And that's why if you get the corresponding equation, the bias 2 will be multiples of the ratio of M1 and M5 multiplied by the ratio of M4 and M3 multiplied by the reference. Looks very complex, but if you divide it, it's nothing but you have corresponding stages and you just do it one by one. Any questions up to this point? Shihao? Okay, good. All right. So let's now move on. Okay, what did I say up to this point is, okay, we started off from the fact if you use the voltage divider, the bias point corresponding from the voltage divider will be affected by the VDD fluctuation. You don't want this situation. So what we did was we have introduced the current mirror with the RS as a reference circuit. And we also have defined, in this case, what's missing here is the startup circuit, right? We just assume the startup circuit is already attached. So in other words, if you're going to use similar circuit in your project, make sure you add the startup circuit. Otherwise, the circuit will not function after powering up. So from now on, we have a called the constant GM biasing. From the self-biasing current source, we noticed that the transconductance of M1 is actually written as the IREF, which has this relation. What am I talking about? I'm talking about here. Here we learned that the reference current is shown as over here, and we have little dependency on the VDD with respect to reference. But here, that's what you're seeing here. And how do you know that the ratio of the W of L2 is actually K times the WL of 1? Where's my cursor? Here it is. And noting that the GM transconductance of M1 from the drain current equation, we have seen this repeatedly through this semester, from the drain current equation can be written as what is shown over here. And notice that the D1 is the drain current of M1, is the same as the reference current. Why? Because we have a 1-to-1 ratio between M3 and M4. So the input current and the reference current is the same. So hence the drain current, which is the M1 drain current, which is input current, is the same as reference. So you can replace that into reference current like this. And then you can simplify by inserting this over here. You can simplify it as 1 over Rs. And 1 over Rs, if the K to 1 is actually 4 to 1. Right? That's very interesting. So you have now Rs, which will be defining the GM1. But what was the problem with this circuit? Do you remember? I already mentioned this earlier. By inspecting this current, what was the problem with this circuit? Kadri, can you please give us some insight?
The process temperature, the PTV.
That's right. Process variation and temperature variation affects the Rs value.
Yes.
And correspondingly, the GM will be also affected. You don't want that. So how do you then eliminate that variation? For analog designers, this is also very important. So this is what we're going to learn it. So up to this point, the GM, the transconductance, is only dependent on the Rs. And assuming the Rs is constant and it's independent of the VDD and the V threshold voltage, because you have no threshold voltage or VDD terms in the GM, then you have a constant GM only if you have a constant Rs with respect to the process and temperature. So you did have achieved the GM to be constant over VDD and threshold voltage variation, which is good news, but you still have variation with respect to the temperature and process. So that's the last item. We want to eliminate the effect of the Rs value with respect to the process and temperature. Correspondingly, you are completely making this circuit independent of the PVT variation, right? That's the last topic for today. How do you do that? All right. So we need to make sure that the Rs is constant over, if corresponding reference current is completely independent of the process as well. Now, how do you do that is as follows. If the MOS transistor, for example, the M5 is shown here, is biased by an M1, meaning that you are going to have an amplifying transistor M5, and that is biased by the M1 transistor, right? That's the same as what, this is the reason we are using the bias circuitry, to bias the M5 in saturation with the little effect on the supply changes. And here, if you do the analysis, the overdrive voltage of M1, which is the overdrive voltage of M1 over here, is the overdrive voltage of M5. Why? Because the ratio is the same. Now, the GM1 is the K prime multiplied by the ratio of the aspect ratio of M1 multiplied by the overdrive voltage 1, which is the same, which you can also write same. The GM5 is the overdrive voltage of M1 multiplied by W over L of 5. So this means the GM5 is the ratio of M5 and M6 multiplied by GM1. And GM1 from the previous slide, we have this relation. The K is the ratio between M1 and M2, right? This is the relation over here. Now, we note that the GM5 is constant, right? This is something that we note, something that we have seen. And you can see that the GM5 is independent of the supply changes because you don't see any supply term over here, right? Up to that is something that is okay. But I already said you still have a ratio problem. The problem with the Rs changing, which will affect the GM5. And if the GM5 changes or fluctuates with respect to the Rs, that means the gain of the amplifier will change. So how do you do that? What about if you have the RD connected to the drain of the M5 over here? One application of this constant GM bias is to obtain an accurate gain from a single stage amplifier. And let's look at the analysis here. The gain of this M5, by now you already know, is the GM5 multiplied by the RD, right? We already know that. And the GM5 from the previous equation is looking like this. And if you rearrange it, it means that the AV, the gain, is actually the ratio of M5 and M1 minus 1 minus M over this ratio of M2 and M1 square root multiplied by the ratio of RD and RS. This is a very, very important finding. Oops, sorry. Okay, what is so special about this is that the gain is corresponding to the ratio of two transistors as well as ratio of the resistors. Now, what is so special about it? The absolute value of the transistor or the absolute value of the resistance may fluctuate due to the process and temperature, but the ratio has little effect. In other words, if you have a nearby resistors, one RD and RS, if the RD has a slight process variation that makes, instead of 1 kilo ohm, it became like 1% larger, so will the RS. RS will also progressively have 1% greater. So the ratio actually is constant, although the absolute value changes. Stephen, do you understand what I'm talking about here? The absolute value may change, but the ratio will have less effect, right? So that means that even if you have a process and temperature variation, because you're relying on ratio, not the absolute value, the AV now will be constant. That's an important finding. So gain is determined by device parameter ratios. In here, I emphasize on the ratios, not the absolute value. And practically, the gain will be controlled within % accuracy. That's quite accurate. Okay, any questions so far? Chihao? Or Celine? Brandon? Then I have a question here, if you really understood correctly. Do you see any potential issues with this circuit? Andre, I think you know the answer. Okay, I'll give you a hint. RS and RD. Okay, let's simplify it even further. RD. When you see the amplifier and transistor with the RD, what's the problem? Oh, sorry, I can't hear you. No, Andre, you already know this. Come on. We have a passive RD on the drain of M5. If you want to increase the gain, what do you need to do? If you want to have a higher gain, okay, I see someone have a chat window. Small output swing, great, that's right. That's actually the problem, right? If you increase the RD, we have learned about this over and over again, right? Correspondingly, having larger RD will increase the gain. However, that will increase the voltage drop across the RD. That brings down the output bias voltage. The swing will be reduced. However, if your application that you're referring to can tolerate that smaller swing, but you care more about accurate gain, then you should use this circuit. But if you're concerned about the voltage output swing, you shouldn't use this because the RD will limit your voltage swing. You should replace RD with the active circuit, active load. Right? Is that clear? So now you can see that the information or the knowledge we learned throughout this semester, we are synthesizing everything together. Right? This is an important finding. And Gary, did you understand what I'm talking about here? Okay, good. Let's move.
But I have a question. So
yes.
So all of these transistors and resistors just to bias the VB, like the one that we had in the beginning.
So in other words, correct. All of these circuitry is actually to generate and bias M5, in other words. But of course, if you have in multiple stage amplifiers, that like sub-project number 3, right? You have multiple stages to operate. So how do you, in that case, how do you actually do? Is you just simply copy this into the another stage, and then copy that to the third stage, and etc. You can see that, right? You can use the same bias circuitry to bias many, many different branches. And don't forget, you have to add the startup circuit, right? Here, you need to have a startup circuit attached to this.
Okay.
Right? That's something that you often forget.
The one that you explained before, right?
Yes. What I mean by it is this. The startup circuit, M5, M6, and 7. That must be added. Okay, so actually that's it for today. So to summarize, we have a simple current source bias circuits are subject to the PVT variation, meaning that if you just have, let's say, voltage ladder as the biasing circuit, you will have the supply changing, which you will have. Believe me, you will have supply changes that will strictly impact the bias voltage, which will impact your drain current, which will impact your gain, and it distorts everything. So the goal here is to minimize such variation. And how do you do that? You can use the self-biasing current mirror to generate the supply-independent IREF, right? That's what we learned. But remember that self-biasing current mirror still is dependent on the process and temperature variation because it relies on the absolute value of the RS. So to remove that, we can actually add the voltage ratio, the ratio of the circuit to be dependent on the IREF. IREF to be dependent on the ratio of the devices, which will be much more accurate. And we shouldn't forget these old circuit that we are talking about today requires the two stable point. It requires the startup circuit so that the stable point in 0 volt and 0 current should be brought up to the intended operating point at the power on. But once power on, the startup circuit has to go to disable itself. Otherwise, it will be an overhead in terms of power. Okay, and self-biasing current mirror can provide both supply-independent current source or current sink. Current sink means that you're just sinking the current so that you have the PMOS as the amplifying transistor. Current source means that you are using NMOS as the amplifying transistor. Probably you already know that. And we can also expand that into the constant GM bias circuit to bias the transistor so that the GM is also constant and only dependent on the RS, and even you can make it such that you only rely on the ratio of the RD and the RS. Right, that actually ends today's lecture. I have a question here. Sub-project 3, we will have the amplifying circuit first stage and second stage VB being connected to the biasing circuit. At the same time, it has a startup circuit, so we have a total of 3 circuits in this sense. That's right. This is what I'm asking you to do. So this is what you actually need to do, and make sure that you have simulated so that the startup circuit is also functioning normally. Any questions so far for today's lecture?
I have a question, bro. So what would the disadvantage be if we use like one transistor and one resistor, as we learned like 2 lectures ago, to bias the M5?
Can you clarify once again?
So I think like 2 lectures ago, we learned a way how to like bias a circuit by using one transistor and one resistor.
Yeah, that's right. So the downside of it, if you can make it in the report, the downside of it is that it will be impacted by the process and temperature variation, as I said, right? But if you can tolerate, that's totally fine. So my advice is that first of all, use the circuit that you have already designed in subproject number 1 and 2 to form subproject number 3. And if you have free time, some of you will have some time, then try to generate the reference circuit yourself by the knowledge you learned today, and then you make it an extra there. Make sure in the report you have clearly stated, okay, I did some extra miles to do this. Right. Any questions?
Prof.
Yes.
For the previous slide, right? Is the V out the VB that we are generating?
What was the question again?
Is the V out on the right the VB that we are trying to generate?
No. V out is actually the, okay. Let's do the exercise here. If you have this new circuitry, what do you need to do? Don't panic, right? And then what did I say? Where's the input and where's the output? Input is in M5's gate. Output is the drain of M5. Then what does M5 do? This is an amplifier. And what is the gain of the amplifier? It's the GM of M5 multiplied by the output resistance, which will be RD in parallel with R05. And RD is smaller than R05, so practically the gain will be minus GM5 multiplied by RD. So the answer to your question is we are providing the input bias, DC bias point of M5. That's the answer. So VB is actually the gate voltage of M5. Is that clear to you?
Oh, okay. Thank you.
In other words, how do you connect this to an input source? Of course, you don't want to disturb the bias point. You need to have a large DC blocking cap, and you have your signal connected. That's basically how you're going to amplify. Let's say your audio signal, you're going to amplify your voice. This is your microphone connected to the large DC blocking cap, which will be input to the M5's gate, which will be amplified and going out through the Vout. Okay, is that clear? Okay, I still see some chat windows right now. I have, oh, you got it. Okay, that's good. All right, so just to summarize, today's lecture is, this is it for today. And don't forget, next Friday at 12 p.m., we have a summary lecture. This is optional. You don't have to come, but I highly recommend you attend. This is an in-person lecture. The lecture venue, as announced, is different from our normal lecture venue. It's actually in the same building, E5, but it'll be in the second floor, E50232. And what we'll do is that we will go through lecture 1 all the way to lecture 10. And we'll do the summary, and then subsequently we'll have a Q&A session if you have any. All right, so that's it for today. Thank you for attending. And if you have any further questions, let's do that on Friday, next Friday. And there'll be no lecture this Friday.
Okay, next Friday is like next week.
Next Friday.
Yes.
Hi, Prof.
Yes.
Sorry for crashing this lecture, but it's Jue Feng here. Yeah. Do you receive the report? Cause I think Joanne sent it out. Yeah.
Oh yeah. Okay. We can do that after I stop recording.
Okay, sure. Thank you.
Yeah. Okay. Let me first stop recording.
Recording stopped.
Okay. Yeah. Yes, I did receive it. Thank you.
Thank you, Prof. So and also is this Wednesday's meeting also at 3 p.m.
No, this Wednesday we cannot have it at 3 p.m. I will make an okay. For the rest of the group, this is irrelevant. He's talking about FIP, so you can leave now. You don't have to stay unless you have a question.
Yeah.
If you have a question, you can ask me now. But to answer that FIP question to Yu Feng, we will probably have it tomorrow. I will make an announcement to my group. So, but we cannot have it on Wednesday because I'll be on aboard the flight.
Oh, okay. So I just asked one of the PhDs for timing.
That's right. Thank you.
All right. Thank you so much. And I'll see you on next Friday, I'm guessing.
Sure.
Okay. Thank you so much, Prof. Thank you.
Thank you. And the rest of the group, thank you for turning on your video throughout the lecture. I really appreciate that. If you have any questions, let me know. Otherwise, you can leave.
Prof, I think Sweetheart asked a question in the chat.
Okay, hold on. Let me check that. Let's see in the chat window. Okay, so for subproject 3, you can use the simple current mirror to provide a bias voltage, but if you have time, you can use the self-biasing circuit source to into lecture. That's right, for the input pairs. That is correct, yeah. All right, any more questions? You don't have to stay, you can go now.
Prof, I have a question about the startup circuit.
Yes.
So we're using 3 transistors for it. Does the W/L ratio matter at all? Or we can like arbitrarily choose any size?
That's right. So let me get back to that. Okay, let me share my screen again. To answer your question, actually matters a little bit. So for example, if you, I will not go deep dive into this because it's out of the scope of this lecture, but just to give you some background, there is a switching threshold. What do I mean by switching threshold is how far do you have to increase the gate of M5 so that the inverter will flip its polarity. That's called a switching threshold. This is different from the threshold voltage of a transistor. And when it comes to the switching threshold, if you have the NMOS, in other words, the M5 greater, then the switching threshold will drop. And for this, as far as the startup circuit is involved, you want to make sure that the switching threshold inverter of this inverter will be low so that it starts up quickly. So that means, practically speaking, for analog designers, we design in a way that M5 is much. But it actually doesn't matter if you have, let's say, a normal inverter will have a ratio of 2 to 1 for all process. These days, it will be 1 to 1. even if you drew that way, the only difference will be it'll start up later. Instead of as soon as you start up, I mean, you switch on the circuit, you'll have a slight more delay if you don't do that way. Yeah, does that answer your question? Yep. And there's another thing that I can tell you. This startup circuit is a totally overhead for normal operation, not only in terms of power, but also in area. And what this startup circuit does is that it just leaks away the current in M5's gate so that the gate at the startup of M3 will drop in voltage. So you want to make sure that the aspect ratio of this M5, M6, and M7 relatively much smaller than your amplifying transistors, because this will be an overhead during the normal operation. Okay, any more questions? All right, so I think you don't need to stay now then. Unless you have a question, you can sign off. Thank you and see you next week. Bye.